So we're the wireless invaders, and our project is called Cardio Count. And in this project, we looked at many different factors that can determine whether a patient has heart disease. So a little bit about our project. Over the course of 3 weeks, we learned Python and machine learning from scratch to produce an analysis of the symptoms that can determine whether a patient has heart disease. The two data sets that we use to create the project are a heart disease data set and a heart failure data set. The main question we were trying to answer while creating this project was, what symptoms best determine whether a patient has heart disease? This project will benefit people who are at risk for heart failure and doctors who want to give high-risk patients prevention plans before any treatment is necessary.
Hi, my name is Manna, and I'm going to be talking about our exploratory data analysis. So we used two data sets from the website Kaggle, and we coded different models to show the relationship between different variables that could potentially cause heart failure or heart disease. So this way, users can look at these models and compare their own data and see how it compares with many other people's data. So our first data set was a heart disease data set, and we created 3 models. The first one being age versus resting blood pressure. And if you hover over our points on the graph, you can kind of see more information about them. And so in this first graph, you see a lot of the yellow dots are clustered around the ages above 50. And those yellow dots represent people who have heart disease, and the blue dots represent people that don't. And you'll see that a lot of the yellow ones are clustered around people that are older. Our second graph represents the relationship between maximum heart rate and resting blood pressure. Here you could see a lot of the blue dots are clustered around the higher heart rates, and you'll see that most of these people are also younger. And a lot of the yellow dots are towards people that have a lower maximum heart rate, and a lot of these people seem to be older than 50. Our third model for this data set compares heart disease and different chest pain types, and also the differences between the male and female and the way they both have these types of chest pains. And you could kind of compare how that affects heart disease. We also used a second data set that has a few different types of variables. And here we created 2 models. The first one being age versus creatinine phosphokinase. So that is an enzyme that regulates ATP, and abnormal levels are often associated with muscle failure. So using this graph, we can see how those levels kind of change throughout your life and whether those people in this data set experienced heart failure because of that. Our second model shows a relationship between age and platelets. Platelets determine your blood health. So you can also see how those levels may change throughout a person's lifetime. And you can also see how it's related to the possibility of having heart disease.
This is the machine learning process behind our data set. We use support vector machine, also known as SVM. It's a model used to solve classification and regression problems. The model attempts to separate data into classes by drawing separating hyperplan. This achieving perfect separability is rarely possible, so the restriction on separation are loosened to achieve a good enough model. For the first model, the heart disease confusion matrix. For those who don't know what a confusion matrix is it organizes data by positive/negative responses and false positive/negative responses. This data had a 78.6% accuracy, which was fairly accurate, as our goal was to have the least amount of positive or negative responses as possible. The heart failure confusion matrix had an accuracy of 83.3%, which was appropriate for our project once again. We also did the K nearest neighbors. The K nearest neighbors, otherwise known as KNN, is a model that makes classification for each point based on their proximity to other parts of classified classes. By analyzing 30 values in the hyperparameter list, we built an optimized model to predict heart disease. The KNN model grid search, the index 12 had the least amount of testing errors compared to other values. This argument will be the most useful for our project since we want to use values that have the most accuracy. The K-12 NNN model assessment had a 65% accuracy. Since we weren't able to detect any accurate negative indicators of heart disease, we concluded that this model would be a perfect for our data.
So for our data set, we also created some decision trees. Decision tree models sequentially partition data. Visually, lines are drawn between groups in the data until all observations have been classified to prevent overfitting, so that the fully grown tree can be pruned. For our heart disease data set, so it was really accurate that it can tell if a person has a heart disease or it doesn't, but it is really uncommon to get 100% testing accuracy. But because of the high accuracy, we suspect this model is overfit. And for our heart failure data set, so since there's a minimal mistakes done in this model, so our team decided it would be a decent model to use for our data. Since the decision trees were overfit, so we decided to use the random forest we created for our dataset analysis instead. So the random forest algorithm trains a sequence of naive classifiers and makes a classification based on a majority vote. This model used an ensemble of 200 shell trees. For our half failure confusion matrix, it has an accuracy of 85%. It shows that some of our data points were not classified accurately. However, 85% of the data was accurate. And for our heart disease data set, the confusion matrix model has a 90% accuracy, since there are 8 false positives and 7 false negatives, which decrease the accuracy of the model. However, overall, the model has a 90% accuracy, which is pretty accurate. For our heart disease data set, the most important variables were maximum heart rate achieved, exercise angina, old peak, and the slope of the ST segment. And for our heart failure data set, the variables that have the most importance in this data set were injection fraction, the level of serum creatinine in the blood, and the amount of time between the follow-up appointment.
These are the members of our team. Throughout the camp, we all worked on a little bit of everything, so we didn't really have any specific defined roles. This project was a great introduction to Python and data science. We used the internet for research and data analysis. We not only gained some experience with technology, but also learned a little bit about heart disease. We compared different variables and diagrams to see relationships between factors that could lead to heart disease. Lastly, we also started to pay attention to the accuracy of our data. Overall, our models worked pretty well. The KNN model was the worst, only having 65% accuracy for both data sets. The SVM model was better, but the random forest model was the best. Important variables were maximum heart rate, exercise angina, old peak, ST slope, ejection fraction, serum creatinine, and the amount of days for a follow-up.
Our most accurate model was the random forest model, averaging an accuracy of 87.5%. The SVM model was the second most accurate with an 80.95% accuracy. The KNN model was the least accurate since it wasn't able to identify any accurate negative indicators. We were able to answer our research questions because we were able to identify a proper model that can analyze the most significant factors having to do with predicting heart disease. We hope that our models can be used by medical professionals to help diagnose heart disease before it becomes problematic. But of course, anyone else can use this too. In the future, we'd like to add a website feature that uses our most accurate model to predict the risk of heart disease given user input. We believe it would be cost-effective for those who have a suspicion that they may be at risk for heart disease, because there would be an online resource available for them to access. We may also want to build probability models so a user can have some idea of their risk. We would like to thank AI Camp for teaching us engineering and data skills over the course of 3 weeks. We would also like to thank our mentor, Hyrum Hansen, and our leader, DSI, Cameron Jackson, for assisting us through the whole way. Thank you for listening to our presentation. Feel free to ask any questions.